Alrighty, let us get started for today. So, what we're going to do is we're going to continue talking about electricity, but we're going to shift topics from talking about the electric force, the Coulomb force between two charged particles, and now we're going to talk about circuits, some basic circuit analysis. Now, obviously, circuit analysis is a very big subject. There's careers based on it. But what we're going to do is kind of introduce the topic, talk about circuit diagrams, how do we draw circuits in a way that is efficient. You know, we don't want to actually have to draw exactly what a circuit looks like in real life, because that would take a lot of time. But we want to be able to draw a circuit clear enough so that when someone looks at the drawing, they know all the parts of the circuit, they can analyze it, they could theoretically predict what would happen if it's turned on or turned off, and all sorts of stuff. And as I said, this topic is a fairly broad topic, and we're going to stick to the basics. As you progress through the physics or engineering major, you're going to get more and more into the subject. So when you get to general physics, of course, we'll talk about some more complex areas of circuit analysis, but even that is still going to be based on kind of the basics. Then there is a class, Physics 323, which is a whole semester just on circuit analysis, where I go through all of the analytical techniques used for analyzing a circuit. But that course is pretty much focused on DC circuits. And we'll talk about what this means, DC versus AC. But it's like if you took the topic or the subject of circuit analysis or electronics, you could divide it in half. Half of it is DC, the other half is AC, and the more modern is AC, of course. And so you get more into that as you progress, if you're going to be an electrical engineer or things like that. But the point, I guess, is to introduce the topic, allow you to figure out the terms, get used to it, get comfortable being able to draw circuit diagrams, and understand the basics of the mathematics behind it. That way, when you start looking at the subject in slightly more detail as you progress through, it won't be such a surprise. It won't be something new. You'll be ready for it, basically. So with circuit analysis, as I said, there's two big overarching varieties. There's what's called DC, which stands for direct current. And then there's AC, which stands for alternating current. Well, the difference between these is basically how the electrons which flow through the circuit, that's what the electricity is, basically. We call it a current. Current is the flow of these electrons through the wires. And the difference between DC and AC is how do the electrons flow in the wires? Either you'll have a circuit. So let's say here's my circuit, draw a little basic picture here. And if this is the starting point, then the electrons flow in one direction and they keep flowing all around the circuit, cycling around over and over again. That's called direct current. You're pushing the electron, or something in the circuit pushes the electrons through the wires, They move through in one single direction, and they just go all the way through the circuit, coming back to the beginning and back again, circling around, which is where, of course, we get the term circuit. Circuit in electronics means this, but of course, you could talk about a race circuit or things like that, or a salesman making his way through the circuit. Basically means there's some path, you visit all these areas, and then you come back to where you started. That's making the circuit. That's DC. Well, AC is different. What AC means, alternating current, is, let's say there's the beginning, is, of course, we know if these are wires, metal wires, copper, or something like that, there's already electrons all throughout the wire, right? It's not like all the electrons are stuck here at the center and then we're shooting them out like a bullet. This is metal, and in metal, you have electrons, just like any material. And so there's already electrons everywhere in this circuit, just sitting there ready to move. And so what alternating current does is it says, look, instead of trying to take the electron that's sitting here right at the beginning and push it all the way around the circuit, all the way back again, which is what DC does, and in doing so, every other electron in the wire gets pushed along as well. Well, that takes a lot of work. You physically have to push this electron this full distance. Well, what if we did something different? What if instead we only pushed the electron a little bit and then pushed it back the other way, or pulled it back? And so you have electrons moving back and forth all throughout, like jiggling, all throughout these wires. Okay? You still have the electrons moving through the circuit in a way. A single electron may start here. It won't go all the way around, of course. It's going to stay there. It's going to move a little bit up and a little bit down. And then the electron way over here in the circuit, he is going to move a little bit up and a little bit down. So every part of the wire, every part of the circuit will feel an electron moving through it, even though technically speaking, the electron never really leaves its spot very far. And that's what alternating current does. Now, why we have the difference between these two, why didn't we just stay with the first or stay with the second? That's a technicality. That's it has to do with efficiencies. It has to do with losses in energy. For instance, if all we had was DC, well, DC works great for circuits. If we have a little piece of electronics and we, let's say we have a radio or a light bulb and we want to light the light bulb up, we start with a battery or, our power source, and we hook up a little DC circuit and it works perfectly fine. However, if what we want is to create a bunch of electricity and send it over to people's houses so that those people can use it to power their electronics in their home, well, now what you have is, here's the power station and you have a bunch of long wires, power cables going from the power plant, the electric company, over to people's houses. And remember, with DC, what's going on is you're physically pushing these electrons all the way through from beginning to end. Well, that takes a heck of a lot of energy. And it turns out that it actually takes way more energy to do it by the DC method than the AC method. If you try to transfer the power by AC, by jiggling the electrons rather than physically pushing them all the way through, then the amount of energy you lose in this traveling is a lot less. And so AC is a great way to move electricity around, move power around, and not lose as much. If we had to do it by DC, then we'd lose a heck of a lot of energy out into the air for nothing. And there's other reasons too. We find out that the fact that the electrons move in two different directions, up and then down or left and then right, allows you to do interesting things and create new components that could put into your circuit that you can't do with DC, since everything moves in a single direction. So there's a lot of reasons to do AC. AC is more complicated, however. The analysis of it is harder to do. The mathematics behind it is harder to do. And at the end of the day, when you have an actual physical thing that you're trying to power, usually you're going to have some kind of an adapter, or let's say an adapter that will transform the AC part of the circuit to a DC part, even temporarily. You may have an AC going through most of your circuit, but then at the critical juncture where you're going to power on a light bulb, there may be something that says, okay, take that AC, turn it into DC for now. We'll do DC for this small part of the circuit, and then afterwards, we'll go back to AC again. So for instance, if you've ever worked with, or played video game systems, you always have those big adapters that you plug into the wall. Instead of it just being a normal power cord, it's a big brick or a big, square thing you plug into the wall. That adapter, a lot of times, changes the electricity that's coming into your house, which was AC, with a certain voltage and a certain current, and it'll transform it in certain ways. And one of the ways it can do it is by changing AC to DC for the use of powering on the system. Then once you're done, or once it's gone through the system back to the wall again, it'll transform it back to AC to go back through your walls to the next part that you're trying to power on. Okay, so DC is very good for doing what it does, for what we need it to do. However, for traveling purposes and for more interesting modern devices, AC is more necessary, just because of the fact that the electrons change directions, let's say. But we're going to deal with DC. DC is more simplified, more basic, more easy to understand, but still has most of the analytical techniques built into it. So we can learn the techniques for analyzing a circuit with easier versions, DC. And then if you want to get into this career or deal with electronics or whatever the case may be as an electrical engineer, then you could use those ideas and those tools when you start learning about AC stuff and a more complicated, complex, interesting circuits. So with DC, what do we need to know? Well, as I said, DC, direct current circuits, you have wires. Through the wires, electricity will flow. And when I say that, what I mean is you actually have charges, charged particles in the wire, in the material, moving along. And we define the current to be, how do I want to say it? We'll say it is the change in the charge per time. Okay, if we want to start looking a little mathematical, we could do it with calculus. dq dt is another way of writing delta q over delta t. But what it means is, if you're going to have a wire here and you look at a chunk of wire right there, and you just detect how many charges come in and how many charges go out per second. That is a measure of the flow of the charges through the wire. And that flow of the charges through the wire is defined as current. The variable for current is I, and its units are going to be amps, capital A for amperes, or amps for short. Okay. So now, this is a very big point of frustration, at least for me and for a lot of people. For some reason, the word current has the variable capital I as its symbol, which of course already doesn't make sense. But then what gets even more, well, I'll say interesting, frustrating is another word, is that depending on the course you take, how advanced you are in this subject, are you doing it from a physicist's point of view or an engineer's point of view, this symbol will change. Sometimes you'll see it as little I for current. Okay, well, that's fine. Big I, little I, who gives a crap? Well, the problem is engineers say, hey, look, little I is good. But if you notice, physicists use I for the imaginary number, right? In mathematics, square root of -1, we refer to as I. And so we can have things like 3 plus 2I. You know, that's a number. That's called a complex number, an imaginary number. And so using little I for current and little I for the imaginary number is bad, because especially when we start getting into AC circuits, we use complex numbers. And so there could be a confusion. So what tends to happen is physicists then will change current to be J, either little j or capital J, especially when they get to high level electricity and magnetism. But then engineers will say, no, we'll keep little I for the current, and instead imaginary number will now be J. So this is a big point of frustration, especially if you're a physicist who takes engineering courses, or you're an engineer who takes physics courses. Because let's say I take AC circuits as an electrical engineer. Well, I've gone my physics career calling current I and the imaginary number little I. And now all of a sudden I'm in an engineering course and I see little I sitting there and I think, oh, that's an imaginary number. And they say, no, imaginary number is J. I say, no, J is a current in physics. I say, no, J is imaginary number in engineering. I is the current in engineering. So it can be confusing, okay? I say it not because it'll be confusing in my class, because I'm gonna keep capital I as current. And anytime we have a complex number, it's little I. J is in vectors, I, J, K, the X direction, Y direction, Z directions, J is the Y direction. So there will be complications like this or confusion in this course, but just know that over the years, if you start to study more and more about circuits, depending on who your professor is, are they an engineer or a physicist or a mathematician, they may use different symbols. And those symbols are used all over the place. But for us, capital I. All right. So the flow of these charges through the wire is defined as the current. Now, specifically, what charges? I gave this away at the beginning of the course or the lecture, but there's two options, right? If you have an atom or molecules, but let's say atoms, which make up the copper wire, then you have two different charges. You can either talk about the protons in the nucleus, which are the positive charges, or you can talk about the electrons, which are in the orbitals around the nucleus. One of those two have to be the charges which are flowing through the wires, right? It can't be the neutrons. The neutrons aren't charged. And so this is another slight point of confusion, because Benjamin Franklin, who was the first person to really study this in detail, said, look, I have to choose one of these. He chose the protons. He said, look, if we're talking about current flowing through wires, then it's the positive charges flowing through the wires, which causes electricity. Of course, now we know that that's wrong. The nucleus doesn't change. If you had the protons moving around, then you'd have the nucleus of the copper molecule, copper atoms, constantly losing protons, and so you actually have nuclear reactions going on because your nuclei are changing. You're losing protons. Instead, what gives rise to the current is the electrons flowing through the wire. It's the negative charges. So what the confusion comes in is because Benjamin Franklin chose protons in his theory of how currents work originally, then every time you draw a circuit and you say, okay, here's a starting point, here's my wires, and the current flows this way. Okay? Well, really, in reality, what's happening is the current, the actual current, flows the other way. Okay? Because he thought it's the positive charges moving around the circuit, but it's not, it's the negative charges, then the model, the analytical model we use to show the current assumes positive charges flowing in one direction. We now know in reality it's the negative charges flowing, and so they have to be flowing in the opposite direction for everything to make sense. So here's one big point of confusion for most people. If we say the current flows clockwise around the circuit, analytically speaking, in terms of the math, in reality, if you actually got a microscope big enough to look at these electrons and see how they flew through the wire, you'd actually be seeing the electrons flow counterclockwise. Okay, so this is more of an intuitive problem, a visualization problem, but we don't really worry about it that much. We say, yeah, that's true, but in terms of the math, we're just going to avoid all of the confusion. Do the math, you get the right answer. Whether physically speaking, the things were moving this way or that way, who cares? We're not going to look at it. All I care about is being able to analyze it and get an answer out of it. But know that this is true. The definition of the current has the implication that it's the protons moving through the wires in a certain direction. The reality of the situation is actually the opposite. It's the electrons flowing in the opposite direction. And over time, physicists just decided to stick with the original thought and not worry about changing it. And so that's the way things are. All right, fine. So that's current. That's what we need to know about current. It's the electrons flowing through the wire. You have more electrons flowing per second, you have a larger current. You have just a few electrons flowing per second, you have a small current. All right, no big deal. Next thing we need to know. So that's the first big thing. Well, what about how are the electrons flowing through the wire? Why would they flow through the wire? Why don't they just sit there on the atoms and do nothing? I mean, that's usually what's done. Generally speaking, elementary particles don't like to be energetic. They don't like to move. They want to be in the lowest energy state possible. So you would imagine that if you had a circuit, a copper wire with things plugged into it, you'd imagine it would just sit there forever. And in fact, it would, unless you power it. And when I say you power it, you either plug it into the wall, okay, or you plug a battery into it or something like that. You have to feed it energy. Well, if you feed it energy, then this, whatever the energy source is, battery, wall, whatever it is, acts kind of like a pump, pushing the electrons around the circuit. And that is called the voltage, capital V, voltage. The units of capital V voltage is capital V volts. Pretty easy. Okay. And what the voltage is kind of like a measure of how hard you're pushing these electrons through the circuit. If you have a very big battery pack, it can really push a bunch of electrons through really quickly, then you have a high voltage. If you have a weak battery pack or a weak power source, then it can't really push that many electrons at the same time. Now, what it is in reality, a voltage, if you think about it in terms of electricity and magnetism, what you learn is that it's really, because we're talking about charged particles, let's say we have a wire like this. And of course, there's electrons everywhere in this wire. Okay. Well, they're just going to sit there. They're kind of pushing on each other in all directions. And so they balance and they just sit in the same spot this whole time. If, however, I have a battery over here, which has a positive side and a negative side, and I plug the battery in, well, what's going to happen is these electrons being negatively charged are attracted towards the positive side of the battery. So they're going to start flowing. They're going to be pulled towards the positive side. And the negative part of the battery has a whole bunch of excess electrons sitting there. They're going to start flowing through this wire, pushing these electrons through as they get attracted to the positive side. And you have this cycle form. Okay, so the way a voltage actually works is nothing more than having positive charges on one side, negative charges on the other. And so the electrons in the wire get attracted towards the positive side of the circuit. And your battery or your power source is supplying this voltage difference. It can give rise to a really high potential, a high positive charge sitting there trying to attract the electrons through, so you'll get a bigger current to flow. If your potential is very small, you have a little bitty positive charge sitting there, then the electrons aren't attracted as strongly, and so you have a small current flowing. Okay? But at the end of the day, a voltage is caused by some power source, whether it be a battery, a plugs, a nuclear reactor, whatever it is, that supplies the voltage. The voltage is what creates the current. Now, the last piece, of course, is called R. It's called the resistor or resistance. And the resistance, that's not capital R. The units is an interesting symbol. It's the Greek letter capital omega. It kind of looks like a horseshoe. And it's called ohms. And these are things you could put into a circuit which will slow down the current in some way. It resists the flow of charges. So if you just have a wire and you plug in a battery, the electrons are going to flow through that wire and just keep on going nice forever until the battery loses its power. But what we can do is plug stuff into this wire, which will try to restrict the flow for some reason. I don't know why we would do it, but we can. And so you may have this circuit flowing, and then we stick something in here, which is a whole bunch of wire coiled up. And then it just keeps on going and going and going. And so there's our battery sitting there. It's going to push the electrons through. And then it reaches this weird thing, which is just a big coil of wire. So imagine, remember, you're this battery trying to push these electrons through, which is fine. But then all of a sudden, someone puts a whole bunch of excess wire, like 10 miles of extra wire into your circuit. There's that much more stuff you have to push through, more friction to overcome, more material to push your electrons past. It becomes a lot harder to do. So by putting this thing into the circuit, you're restricting the current, because all of a sudden you as the battery have to do a lot more work. You only have a certain amount of energy to use. So now, since you can't push hard enough to make it through as fast, the current is now slower through the resistor or through the circuit. Now, again, I haven't told you why we would do it. It doesn't matter why. This is just something that can be done. And if we do this thing is called a resistor. It gives rise to a resistance, and a resistance is just trying to constrict the flow of the charges. It reduces the current. And those are the three things we need to know. All three, that's it. In every circuit we're going to draw in this course, and when we talk about DC circuits in general, these are the only three elements that can be in a circuit. A voltage source, which is like a battery, the current, which are the electrons in the wire flowing around, and resistors, things we can put into the circuit, which makes it harder for the current to flow. And anything we put in the circuit will always make it harder to flow, unless it's an extra battery. Put extra wire in there, there's more wire, it's harder to flow. We put a light bulb in, the way the light bulb works makes it harder for the electrons to get through. We put a radio in, again, there's more stuff inside the radio, harder to get through, it's a resistor. Everything's a resistor. All right, now, obviously, as I'm saying this, talking about plugging in a light bulb or a washing machine or a radio, when I go to draw so I can analyze a circuit, I don't want to have to draw what a radio looks like. I don't want to have to draw what a washing machine looks like. I'm not a good artist. So instead, what I want is a way of being able to draw these circuits in such a way as to understand what all the pieces are, but to make it as efficient and basic looking as possible. And so we have symbols that we use. The first symbol is for the voltage, V. A voltage in our class, and for the most part, which is a battery pack, a power source, the wall outlets, whatever it is drawn like this. You have two lines, one longer than the other, and then you have the wires sticking out of it. Okay, so you can think of that as like battery. You have a positive end and a negative end. And that's the pump, which is going to push the electrons through our circuit. And this is the symbol. Okay, so if we have a circuit, this is what it would look like. This is the voltage source. So the power supply, the battery, whatever it is. And then the rest of the line is just the wire connecting the voltage source. Current, of course, there's no real symbol for current, at least at the level we're going to talk about. You can think of it as just the arrow flowing through the wire. As you get to more complicated circuit analysis, we won't do it in this course, but in general physics, we'll see it. There is a current source, which looks like this. Okay, it's an arrow with a circle around it and then the wires coming out. This would tell you that there's something in your circuit causing a current to flow there. It's different than a voltage source. This is a current source. So maybe you have some really big complicated circuit and you're going to look at a small piece of it, right? So if you have this huge circuit with a whole bunch of stuff going on, and we only want to look at what's going on right here. So what we would do is we would analyze, like, okay, there's some current source coming into this thing. And then we have the rest of the circuit going on, whatever is happening here. And then it goes back. Okay, so this part stands for everything that came before that part of the circuit. It's like stuff was happening. I don't know what it is, but at the end of the day, what it means is you have a current coming in of this much. Don't worry about how we got it. That's what's going on. So that's kind of like what this symbol would do for us. It's just to tell you at this part of your circuit, I know the current is this much. All right, so it's different than a voltage source. The voltage source causes the current to flow. The current source is like, I know, however I know it, don't worry about it. I know that in this part of the circuit, you have this current flowing. All right, so get rid of all that because that's not really important. We're not going to deal with current sources this semester. The last symbol is the resistor. And a resistor is a symbol that looks like this. It's like a jagged wavy line. Okay. That's what a resistor symbol is. So if you have a circuit, here's our voltage source, and then here's a resistor, and then the rest of the circuit. That's a nice basic, the most basic simplified circuit that has all the pieces you need to analyze it. You have some resistor R, you have some voltage source V, and then we can start asking questions. We can analyze it. We could say, for instance, what must be the current which would flow through this circuit? Because you have a voltage source which can give rise to some current, but then there's a resistor sitting there, and I know resistors restrict the flow of current. So the fact that the R is there means whatever the current could have been, it's now going to be less. So what is it going to be now? Or we can ask, what's the power of the circuit? Power, of course, being like a measure of how much work is done per second or how much energy do you lose. And so that's important, of course, if you're talking about electronics and you need to power the electrical device, you need to know how much energy is this thing going to use up every second to work. Because if I have a little bitty battery, maybe it's only going to last 10 minutes. If I have a really good battery, maybe it'll last a whole day. But that's it. These three symbols, and the only two we're going to use is a voltage source and a resistor, is all we need to do our analysis. All right, so let's do a quick, easy example. Here's an example. You have a circuit, which looks like this. This is a 10-volt power source, and you have a resistor of 5 ohms. The question is, calculate the current and power of the circuit. Well, how do I do this? Obviously, in order to answer a question like this, we need to have some equations. We need to know a relationship. I know that the size of a voltage will give rise to certain currents, and the bigger the voltage, the bigger the current, generally speaking. And I also know that resistors take away current. They reduce the current. So if you have a big resistor, your current's going to be reduced a lot more. But what is this relationship? Well, it turns out that there's a particular equation, and this is called Ohm's Law. Okay, named after Mr. Ohm. And Ohm's law says that the relationship between the voltage, the current, and the resistance of a circuit is V is equal to I times R. A nice, easy relationship. If you want to know the voltage you have to use to have a certain current flow, then you say, what's the resistance of my circuit? What kind of current do I want? Multiply those two numbers together. That's the kind of battery I have to stick in this circuit. Okay. Now, there's a second relationship we need, which is for power. And I'll go ahead and give it to you now. Power is defined as the current flowing through your circuit times the voltage source used to create that current. Okay, so two relationships. Ohm's law, V equals IR. Very easy. The power law is I times V, the current times the voltage. Now, this particular relationship, you're going to see as you progress in many different forms. Because when you're analyzing circuits, you don't always have both of these pieces of information. You may not know the current and the voltage yet. Maybe you know the voltage and the resistance, but you don't know the current. You haven't solved it. And so what people do is they'll combine the power law with Ohm's law to create new equations. So for instance, let's say I take the Ohm's law and I solve it for I. I get I divide it over the R to get I by itself. I becomes V over R. Okay. So that's just another way of writing Ohm's law. Here I've solved for current instead of voltage. It's still Ohm's law though. And what they'll do is they'll take this I and they say, I don't know what the current is in my circuit, so I'll replace it. And so now I have P, and instead of writing I put V over R times V. And so this is V squared over R. That's another way of writing the power equation. The power is the voltage squared over the resistance of your circuit. And then, of course, you could do the same thing with the V. Instead of V, I times V, we could replace V with I times R, and we get power is I times R, which is I squared times R. Okay, so three ways of writing power. And it all depends on what knowledge do you have in the problem. Do you have the current and the voltage? Then multiply those two, you have the power. Do you have the current and the resistance? Then it's I squared times R, and so on. Okay, so I write it like this just so you know, if you look up in textbooks or other places, you may see people use a different equation. This is how they got the other equation. They start with I times V, and they use Ohm's law to replace one of the variables that they don't know. But all I ever do, I just remember Ohm's law, and I remember the power law, and that's it. Everything else I could do mathematically. I manipulate things algebraically, and I get some new equation. So I never have to remember any of that stuff. All I remember is these two. All right, good. So those are the equations we need. That's it for now. So let's solve the problem. First question, what is the current which would flow through this circuit? Well, I have V equals IR. That's my relationship. What I want is I, so I solve it for I bring the R to the other side. I get I is V over R. Do I know the voltage of my circuit? Well, yes, it's 10 volts. So 10 for the volts. Do I know the resistance of my circuit? Of course, it's 5. So 5 for the resistance. 10 over 5 is 2 amps. That's the current which would flow through my circuit. Nice and easy. You take the information from your circuit, plug it into this nice little equation, and you have your answer. What about the power? Well, the power, I times V. Do I know I? Do I know the current? Well, I just solved for the current, so yeah, it's 2. Do I know the voltage? Of course, it's 10 volts given in the problem. So the power is 20 watts. Yeah, I don't know if I said that. The units of power is W, capital W, which stands for watts. It means joules per second, energy per time. But instead of having to write joules per second every single time, people replaced it with a new variable, capital W, which stands for watts. And watts is the unit of power. So if you deal with audio equipment and stuff, you see watts all the time. How good are your speakers? What kind of amplifier do you use? Things like that. You hear the word watts. Or light bulbs. This is a 100-watt light bulb, or these LEDs is it gives as much light as a 100-watt light bulb, but only uses 5 watts of power. Okay, what they're talking about is how much energy does this thing use up every second? The more powerful, the more work it could do. So if you have a machine that could do a lot of work, it's very powerful. It has a lot of power. But in order to do a lot of work, you have to use a lot of energy. So there's a trade-off. So anyway, there we go. Nice basic example. We have a simple circuit that has a voltage source, so maybe a battery, and something plugged into my circuit. Maybe it's a light bulb. And what I know about this light bulb is it resists the current with a resistance of 5 ohms. And then electricity will flow. My electrons will flow around the circuit. And the question is, given this resistor is sitting there, and you have this battery pack, what kind of current will flow through my circuit? And then how much power is used by my circuit? But first, I use Ohm's law. Ohm's law relates the voltage, the current, and the resistance. So I get my current. Power, well, you just multiply current times voltage if you have those. If I didn't, then I'd do one of the other two, V squared over R. I know V, and in fact, we could go ahead and test to make sure it's the same. If I use power as V squared over R instead, well, what's the voltage of my circuit? It's 10, so 10 squared. Over R, the resistance of my circuit was 5, so this is 100 over 5, which of course is 20, same number. So all 3 of these versions of the power equation work. It just depends, what do you have in terms of your information? And then use the appropriate equation. So any questions about this example? All right, well, obviously, if this is all there was to it, everybody would be an electronics master, because this is fairly simple. It's not a big deal, especially the more we practice it. The issue comes in, of course, when you have a more complicated circuit. This was the most basic circuit that had every piece in it. But what if I have maybe 2 resistors in my circuit? Here's a question. If I have a circuit, here's my little voltage source. And now I'm going to plug 2 resistors. Okay, well, here's a resistor and here's a resistor. So call that 10 volts. Let's say this is 7 ohms and this is 3 ohms. And I want to ask the same questions. What's the current flowing through this circuit and what's the power? Well, now, if we're being careful, I don't know how to solve this problem. I mean, of course, I have V equals IR as my relationship, and I know the voltage is 10. The problem is the R, the resistance. How do I figure out the resistance of my circuit if there's multiple resistors sitting there? Now, that seems like a stupid question, a naive question. Obviously, if you have 2 resistors, just add the 2 resistances up and you have a new total resistance. That seems to make perfect sense. However, let's be careful about things, because there's another way I could show that there's 2 resistors in this circuit. What if instead I drew the circuit like this? Okay, much more complicated looking for whatever reason, but still, let's say this is 7, this is 3. That also is a circuit that has a voltage source and 2 resistors, and that's it. Now, do these two circuits work the same way? Well, let's think. Let's analyze what's going on. Take the first one. Let's look at what happens to the electrons as they flow, the current. Well, the electrons flowing through, they're coming along, hit the 7 ohm resistor, and they have no choice but to go through it, right? They have to pass through it. So they get through it finally, and they're on the other side, but then they hit the 3 ohm resistor. Like, oh, dang, now I have to go through a 3 ohm resistor too. But they get through it and go around and come back to the beginning again. Okay, so in the first circuit, every electron not only has to make its way through the first resistor, but also the second. Look at the second circuit. What's going on here? Well, the electrons are moving along. Then they get to this point, and something weird happens. All of a sudden, the electron has a choice. It can either flow upwards through the 7 ohm resistor, or it could flow downwards towards the 3 ohm resistor. But let's skip that for now. Let's say they've done whatever they do, then afterwards they're out of the system and they just continue along the circuit. So obviously the important piece is right there. If we look at a single electron, that single electron either goes through the 7 or it goes through the 3, but it never goes through both. The first circuit, every electron went through both resistors. The second circuit, any single electron only goes through one or the other. Some of them will go through the 7, some of them will go through the 3. So surely, the second circuit does not act the same way as the first, because every single electron that's trying to flow through doesn't feel the full resistance. Some of them feel a 7, some of them feel a 3. Whereas in the first circuit, everyone feels a 7 and a 3, both. So surely they work differently. And in fact, they do work differently. And this is where the complication, all the complication of circuit analysis comes from. It comes from the fact that if we plug in multiple elements into our circuit, there's different ways of doing it, and each way is different, and each way makes the circuit act differently. The first circuit is going to have a lower resistance than the second circuit. I mean, a lower current than the second circuit. The fact that you have one resistor, then the other resistor right after, means it resists a lot more because both resistors are resisting, versus the second circuit where some of them feel the first one, some of them feel the second one, but no electron feels both. So in the second circuit, there's less resistance, and so you'll have more current flowing. So if this is true, then it's not as simple as, well, if you have multiple resistors, just add resistors. Because there's no way that one method works for both of these circuits. These circuits must act differently. All right, so as long as, well, first of all, are there any questions about that kind of conceptual framework? Seeing these two circuits as different circuits, working differently, even though all the elements are the same. Any questions about that? All right, well, if we agree that these two circuits must act differently, then the question is, what methods do we have for combining resistors if there's multiple resistors in a circuit? Because we can see we have two different ways of plugging in resistors here. And so there better be two different methods at least, and maybe there's an infinite number. Maybe every single different way of plugging in 2 resistors or 3 resistors has a new method for doing it. That would suck. Thankfully, there's not. There's only 2 ways. The 2 ways go as follows. When combining resistors, you can either do it in what's called a series way or a parallel way. Okay. Now, technically speaking, there are more ways of doing it, but those other ways, we cannot analyze the circuit the way we're going to do this. There's more advanced techniques you have to learn, which come after what we're doing here. And you learn them in physics. But in this class, we're not going to worry about those more fancy ways. In terms of being able to use Ohm's law and analyze a basic circuit, resistors will either be plugged in series, or they'll be plugged in parallel, or a combination. You can have a circuit which has both series and parallel at the same time. But these are the 2 ways. Now, how do I know the difference between the 2 ways? Series is defined as 2 resistors are plugged in series if an electron must go through both. It has no choice but to go through both. Resistors are plugged in parallel if an electron can choose to go through one or the other and does not go through both. Okay, that's one definition. Another definition that is helpful sometimes is you have to do some fancy footwork here, but we say, let's say you have 2 resistors connected, like the series one here. What we do in a circuit when we're trying to analyze a complicated circuit is everything that's plugged into the circuit, we're going to put what's called a node on either side. So here's a node here on the left part of this resistor and one on the right part of the resistor. And then for the other resistor, here's a node on his left and a node on his right. Okay, it's just a little dot. You stick it on there. And for every single element on the left side and the right side of the element, you put this dot. And so we could do it for the parallel side too. Let's do it. Here's the left side of that resistor, the right side of that one, left side of this one, the right side of that one. Okay. The next rule is if there's nothing between nodes but wire, no other element is sitting there, no other path can be taken, then those 2 nodes must be the same node. Okay, well, with the series one sitting there, there's nothing that looks like that. But for the parallel one, notice this node and this node on the left side, in between them is just wire. So really, this is all one big node. It's not 2 separate ones, it's just one node. And it's the same for the right side over here. Here's a node, here's a node. There's nothing between them but wire. So really, that's just one big node. Okay, in fact, I could redraw this guy to make it clear. This is all coming from one node here and one node here, right? Then the top picture, I drew it as nice square wires and everything. Bottom one, I have curvy wires, but they mean the same thing. You had one wire come in, split it off into 2 things, but those 2 things are connected to each other here at this point. So it's just one node sitting there. Okay, so given the rule, those 2 rules. Number 1, every element gets a node on either side. Number 2, if there are 2 nodes with nothing in between them but wire, then they're really one node. Okay. Once you have those done for the whole circuit, then the rule is two resistors are connected in series if they share only one node. And parallel if they share two nodes. Okay, and let's see if this works for my little examples here. In the series one over there on the left, this resistor and this resistor share that one node in common, and that's it. Resistor one, his left node is over there by itself. It's not touching number two. And resistor number two, his right node is over by himself. But the one between them, they both touch. So those two resistors share that one node in common and only that one node. So they must be in series. Whereas in the parallel case over here, these two resistors share this right side node together. They both have it. And they share this, the left side and the right side node. So both of these resistors are touching both of these nodes. Since they share two nodes in common, those resistors must be in parallel. So that's the second way of doing it. The first way is conceptual. If an electron must go through both resistors with no choice, they're in series. If an electron has a choice and can go through one or the other, but not both, they're parallel. The other way is the pure analytical way. For every element in your circuit, you put a node on either side of the element. If two resistors share only one node, they must be in series. And if they share two nodes, they must be in parallel. All right, any questions about what defines resistors to be in series or parallel? This is a huge, huge, huge thing. Almost everything you're going to worry about in circuit analysis comes from this. This is where all the complication is. All right, well, here's some examples, and I want you to tell me if you think these resistors are in series or parallel. All right, so first example, are these two resistors in series or are they in parallel?
Series.
Series, okay, good. What about these two resistors? Are these two resistors series or parallel?
Series.
Parallel.
Parallel?
Parallel.
Parallel? Everybody think this is parallel?
Series.
That's parallel.
Oh. Aha, we have an argument. I like this. All right. If we were to bet, what percentage of the
series.
Aha, okay. So some more brave people are coming out as thinking this is series. I will say this is series. Okay. And this is, I love this example because it's so easy to think it's parallel because every single time a teacher shows series and shows parallel, they always do it in the same way. Whenever they do series, they show this. It's, oh, that's easy. One thing after the other. That's series, obviously. And every time they show parallel, even I did it, notice right there, I show the two resistors literally parallel to each other. And over here, they're literally parallel to each other. And now over here, literally parallel. But that's a misnomer. When people say the two resistors are in parallel, they don't mean they're literally parallel to each other in terms of geometry. What they mean is these two things can run at the same time. You can have electrons going through one branch and electrons going through the other branch, both happening at the same time separately. So you hear the term a lot in computer science. You have parallel computing. That means you have part of your computer process working on one calculation and another part working on another calculation rather than the old school, which was you make a program, the computer goes, I do this thing, then I do the next thing, then I do the next thing, and you go one at a time. That's where series and parallel comes from. This one on the right is not parallel. How do I know? Well, instead of just looking at it and seeing, oh, parallel pieces, they must be parallel, which is very tempting, trust me. What you have to do is, let's look at it conceptually. If I imagine the electrons flowing through, there's an electron coming along. That electron has to hit this first resistor. He has no choice. He must go through him. All right, fine. He keeps going. And then bam, he has to hit the second resistor. So every electron that flows through the circuit will go through the first resistor and will go through the second one with no choice in the matter, can't skip them, anything like that. Okay, that is the rule for series. Another way of looking at it is, let's do the little node thing. Here are the nodes for the top resistor. Here are the nodes for the bottom resistor. But then if you notice the right side nodes, it's just wire sitting there, nothing in between. So really these two nodes are the same thing. It's one big node, not two. But the ones on the left, I can't do it because there's a little voltage source in between. So if I look at how many nodes these two resistors share, they share the one on the right, but not the ones on the left. So they only share one node in common, thus they have to be in series. And here's a little trick about circuit analysis, circuit diagrams specifically. This picture I drew is the same as that picture. They're identical. All I did was I grabbed onto this guy and I pulled him around, stretching the wire until he was over here. And so that just stretched this piece of wire to create this circuit over there. But if you look at them, they're the same thing. And so in fact, when it comes to drawing a circuit diagram, these two circuits are not different circuits. They're identical circuits. And you could draw it either way. It doesn't matter which way you draw it. They mean the same thing. And to someone who's experienced with circuits, they would look at these two and say, why did you draw the same thing twice? They don't see it as two different circuits. So this is very, very clear example that we have to be careful when we're looking at these circuits because sometimes they're tricky. What looks like it could be one thing actually acts as another. And we don't necessarily see it from our intuition, so we have to be careful as we analyze these things. Because the difference between series and parallel is huge when it goes into calculations. Okay, here's another example. Imagine you have this circuit. And the question would be, series or parallel? Well, obviously here, this is a much more complicated case. I can't just say this thing is in series or this thing is in parallel because there's 4 resistors. Some of them are in series, some of them are in parallel, but not everything is in parallel with everything, and not everything is in series with everything.
Can it be both?
It can definitely be both. That's right. And in fact, what your job will be for this topic is to take something that looks like this and drag it down, modify it in your own mind or by drawing until you get something nice and sweet that looks like this. Because this guy, we could do V equals IR on, right? If we know this R, we know this V, we could calculate I easily. This guy at the top, oh my Lord, resistors all over the place. How in the world do I just use V equals IR? What your job will be, and this is what we're going to learn, is number one, we look at what's in series and we look at what's in parallel. When I see this circuit, I see, look, these two right here, these are parallel. And I'm going to do some math. And in doing that math, what's going to happen is I'm going to convert this thing, which was a parallel set of two resistors, into a single resistor with some new number I'll call all R parallel. Okay, there's going to be some mathematical technique to do it. We'll learn it. But once we've done it, I've now changed my circuit to this thing. And now I look and I say, hey, look, these two guys are in series with one another. So I can do some different mathematical technique to add those two things together. And if I do that, then these two resistors change to something new, which would be some other resistor whose total resistance is something new, call it R3 or something. And then I look and I say, okay, I've got this resistor and this resistor. There's nothing in between but wire. So there's only one node sitting here. They share the one node in common. They must be in series. So now I just get these two resistors, do my series mathematics to change it into a single resistor with this new number. And now I've got that guy down there. And once I've simplified a complex circuit to this thing, now I just do V equals IR, solve for I get I as V over R, and I'm done. Okay, that's our job. That's what we're going to be doing. So what we're going to do next time, now that I've shown you there's a difference between series and parallel, is what are the mathematical tools for series and what's the mathematical tools for parallel. I'm going to use them to take this complicated circuit, simplify it down one step at a time, and it may take 4 or 5 steps of simplification, but I do it one step at a time until I'm left with the most basic circuit, one resistor with one voltage source. Once I have that, V equals IR gives me my answer. Now again, this is the basics of circuit analysis. We go a lot further in other courses where we have really fancy ways of plugging in resistors where neither of these things, parallel or series, works. And then you get to AC circuits where all of a sudden you have new pieces. You don't just have resistors. Now all of a sudden you have something called a capacitor or a diode or an operational amplifier, all sorts of stuff. But for us, this is our job. Can we figure out this basic circuit analysis for series and parallel resistors and get a good feel for it? That way, when we do start to get the more complicated stuff in other courses, the basics is easy and we can focus on the new techniques then. So that's what we're going to do. Next time, I will show you what the calculations are for series versus parallel. We'll do a whole bunch of examples. Thursday of next week, we'll do even more examples. Okay, so I figure Tuesday and Thursday we'll do examples. Tuesday of the following week will be an exam review. And Thursday of that following week will be the first exam. That's looking like the timeline, unless everybody is a circuit genius and we get all the examples done on Tuesday, then we can have the exam review on Thursday. But for now, let's just assume we need 2 more days of examples and stuff, just to make sure it's clear for us. So that's kind of our timeline. This coming Tuesday, we're going to do the series and parallel resistor stuff, do more examples the following class on Thursday, and then the following week is test, review, and test. Okay. So other than that, that's all I have for you today. I know this was a longer class period than normal, but I thank you for the attention. And if you have no questions, you're free to go. I will see you next week.